So, we had completed our discussion of the diffusion equation, basically the Laplace equation for the temperature or the concentration field, or the Laplace equation with a driving force such as a pressure gradient, okay, for the velocity field. And we had examined all of these problems and looked at different ways to solve them: separation of variables, superposition of point sources and sinks, distributed sources, and the method of images. This lecture we will start our discussion on forced convection. I will start with an example of the flow past a flat plate. Okay. We have a flow past a flat plate, okay, and the velocity field, okay, has to decrease to 0 at the surface due to the no slip boundary condition. Okay. The velocity field has to decrease to 0 at the surface due to the no slip boundary condition. Now, perpendicular axis is z, streamwise axis is x, okay, and T temperature in the fluid far from the surface is T infinity. Okay. Temperature in the fluid of the surface for x less than 0 is T infinity, and for x greater than 0 we have a heated section here. Okay. For x greater than 0 we have a heated section where the temperature is T is equal to T wall. Okay. And we have to determine the temperature field in the fluid in the limit where convection is dominant. Okay. So, recall that our equation was V dot grad T at steady state is alpha del square T. Okay. And we had scaled V star is equal to V by a characteristic velocity, okay, x star is equal to x by L, and using the scaled variables we had got the Peclet number times V star dot grad star T star is equal to del star square T star. In our discussion so far we have considered P e to be small. Okay, in our discussion so far we had considered P e to be small so that we can neglect the left side and solve only the diffusion equation on the right side with possibly some sources. Okay, with possibly some sources. Okay. Here we will consider the case where the P e is large compared to 1. Okay. Here we will consider the case where P e is large compared to 1, where diffusion is dominant. Okay. And let us consider that the total length of the heated section is L. Okay. The total length of the heated section is L. Okay. And the velocity in the x direction is Vx. Okay. Velocity in the x direction is Vx. So, this V dot grad T is equal to alpha del square T. I have considered a steady state configuration where the time derivative is neglected. Okay. So, for this configuration this will become Vx partial t by partial x, there is no velocity in the z direction, okay, is equal to alpha into partial square t by partial x square plus partial square t by partial z square. Okay. And the boundary conditions are that t is equal to T infinity for z going to infinity far from the surface, T is equal to T naught at z is equal to 0 for x greater than 0, and T is equal to T infinity at the start of this heated section, okay, at x is equal to 0 for z greater than 0. Okay. So, at the start of the heated section x is equal to 0, for z greater than 0 the temperature is T infinity. Okay. So, those are the equations and the boundary conditions. Okay. Now, how do we scale these? Okay. The simplistic naive way of scaling would be to say that x star is equal to x by L, z star is equal to z by L, Vx star is equal to Vx by a characteristic length characteristic velocity, okay, and T star is equal to T minus T infinity by T wall minus T infinity, okay, in which case T is equal to T infinity corresponds to T star is equal to 0. This is T star is equal to 1. I am sorry, this should be the wall temperature, not T naught. Okay. Okay. And this one is T star is equal to 0. Okay. And if you use the scaling, you will find that Vc into L by alpha, okay, partial T star by partial x star is equal to partial square T star by okay. So, I should have a Vx here. So, okay. Okay. Okay, so that is the equation. Once I have scaled it, this thing is the Peclet number, okay, and we are considering the case where the Peclet number is large. Okay, so we are considering the case where the Peclet number is large. So, I can alternatively write the equation as partial T by partial x. And in this particular case, if I consider the limit where the Peclet number is large, 1 over Peclet number is small. So, you would think that you can neglect this diffusion term altogether. Okay. Okay. Simplistically, you would think that this diffusion term can be neglected. And if the diffusion term is neglected, okay, I just get that partial T star by partial x star is equal to 0. Okay. That is, there is no variation of temperature with the x distance. Okay. So, whatever the temperature is at the start of the heated section, it is going to be the same throughout the domain. Okay. It is going to be the same throughout the domain. Okay. So, the temperature is just going to be T infinity throughout the domain. Okay. That is what you get from partial T by partial x equal to 0. Clearly, that does not satisfy this boundary condition that at the wall temperature is equal to T star is equal to 1 or T is equal to T w. Okay. Clearly, that condition is not satisfied by this equation. Okay. So, what is the problem here? Okay. So, what is the problem here? Problem is that when we neglected this diffusion term, we have neglected the highest derivative. Okay. When we neglected the diffusion term, we have neglected the highest derivative, okay, because there is a small parameter that is multiplying the highest derivative. Okay. So, when we neglected the diffusion term, we neglected this highest derivative, and therefore, we cannot satisfy the boundary conditions. That is the mathematical problem. Okay. Physically, what is the problem? Okay. The problem is that there is the heat the fluid is getting heated due to heat transfer from the surface. We are considering a limit where convection is dominant compared to diffusion. Okay. We are considering a limit where convection is dominant compared to diffusion. Okay. That means that whatever heat is generated from the surface is getting rapidly swept downstream. Okay. Whatever heat is generated from the surface is getting rapidly swept downstream. Okay. Therefore, you would expect the disturbance to the temperature field to be restricted to a thin region close to the surface. Okay. You would expect the disturbance to the temperature field to be restricted to a thin region close to the surface. Okay. And within this region there will be a temperature disturbance, okay, the disturbance to the temperature due to the heat that is coming from the surface. The heat flux from the surface is coming out perpendicular to the surface, okay, and it is getting carried downstream by convection. Convection is strong, and therefore, this region where the temperature is disturbed due to the heat flux will become thin. However, it will not be 0, okay, in general. When we had done the scaling, okay, we had assumed that the relevant length scale for both the streamwise and the cross stream coordinate is L. We had assumed that the relevant scaling for both the streamwise and the cross stream coordinate is L. Okay. However, in the limit of high Peclet number, okay, the variation in temperature is restricted to a thin region close to the wall, okay, to a thin region close to the wall. I will call it as delta. If delta is small, right, then the heat flux, which is the temperature difference divided by the distance, is large, and it could be of the same magnitude as the convective term, provided delta is sufficiently small. Okay. You could have a balance between diffusion and conduction and convection. Okay. You could have a balance between diffusion and convection if the thickness of the layer over which there is diffusion is relatively small, so that the gradients are large and the flux is large. Okay. So, therefore, we have to include diffusion in order to satisfy the boundary condition, or in order to include include the effect of heat conduction from the surface on the temperature field close to the surface. Okay. So, there is a fundamental issue here. So, therefore, rather than scaling Z by L, we should scale Z star is equal to Z by some length scale delta. That length scale to be determined from the condition that convection and diffusion are of equal magnitude within this region. Okay. So, let us do the scaling again. Okay. Note that within this thin region of order delta close to the surface, okay, if I expand out, okay, this thin region of order delta close to the surface, okay, what matters is not the velocity field in the flow, but rather the velocity field close to the surface. Okay. What matters is the velocity field close to the surface. Okay. And close to the surface, okay, you can see that the velocity field, okay, within this thin region is increasing linearly. Okay. Is increasing linearly from the surface, okay, because the velocity has to be 0 at the surface and it has to increase linearly from the surface. Therefore, I can approximate Vx as the slope, okay, at the surface, okay, prime, okay, times z. Okay. So, velocity is increasing from 0 linearly close to the surface, where Vs prime is equal to dVx by dz, the slope velocity gradient at z is equal to 0. Okay. The slope of the velocity profile at z is equal to 0. Okay. So, this has to be our approximation for the streamwise velocity close to the surface. Okay. This has to be our approximation for the streamwise velocity close to the surface. Okay. Therefore, I have to define Vx is equal to Vs prime times z. So, let us go back to the original equation. Okay. Vx partial t by partial x is equal to alpha into partial square t by partial x square plus partial square t by partial z square. Okay. You can write this in terms of t star. Okay. Okay. there is no problem. Okay, because the scaling for t, the equation is linear in t. Okay, so we have equal scalings on both sides. Okay, and for this I write this as Vs prime times z. Okay, and then I have to define x star is equal to x by L and z star is equal to z by delta. Okay, if I will get Vs prime delta z star by L partial t by partial x star is equal to alpha by L square Now, the largest term on the right side is this one. Okay. The largest term on the right side is this one. Okay. If the cross stream diffusion has to be comparable to the streamwise convection, then this cross stream diffusion term has to be of the same magnitude as the streamwise convection term. Okay. Therefore, I can divide throughout by alpha by delta square and I will get Vs prime delta cubed by alpha L z star partial t by partial z partial x is equal to delta square by L square partial square t by partial x square plus partial square t by partial z square. And delta is small, it is much smaller than the length of the pipe. Therefore, I can, this term is 0, that is the streamwise diffusion is much smaller than the cross stream diffusion, because the streamwise length scale is much larger than the cross stream length scale. And convection and diffusion are of equal magnitude provided this is order 1. Okay. Convection and diffusion are of the same magnitude provided this is order 1. Okay. From that we will get that delta cubed okay, is equal to alpha L by Vs prime, okay, or alternatively delta is equal to alpha L by Vs prime whole power 1/3. Okay. So, this is the length scale. Okay. So, this is the thickness of the layer within which convection and diffusion are of equal magnitude. This is called the boundary layer thickness. Okay. Within which convection and diffusion are of equal magnitude. Okay. You can verify that this has dimensions of length. Alpha is length square per time. Okay. It is a diffusion coefficient, length square divided by time. Vs prime has dimensions of 1 over time. Okay. So, therefore, this is has the correct dimensions. Okay. So, this is the region within which convection and diffusion are of equal magnitude, and in that case there is a balance between streamwise convection and cross stream diffusion in this case. Okay. There is a balance between streamwise convection and cross stream diffusion in this case. Okay. Therefore, the simplified equation for the temperature field is Vs prime Z partial T by partial x is equal to alpha partial square T by partial Z square. Okay. Now, there is one other simplification that we use in this case. Okay. There is one more simplification that we use in this case. Okay. That is, at a particular location, let us say x, okay, at a particular x location. Okay. At a particular x location, there is diffusion perpendicular to the surface, that is cross stream diffusion. There is streamwise convection downstream. Okay. There is streamwise convection downstream. Okay. So, there is diffusion perpendicular to the surface and there is streamwise convection downstream. Okay. Since there is convection is downstream and convection is fast, there is no diffusion in the streamwise direction. Note that diffusion is an isotropic process. It takes place in all three directions simultaneously. There is no streamwise diffusion. Okay. Therefore, the boundary layer thickness at a given location x, at a given location downstream location x, the boundary layer thickness at that location can depend only upon x, not on the total length L, because the distance to the total length L is the length to a downstream location. This location x that is upstream cannot be affected by the total length, right. It shouldn't, the boundary layer thickness at a given location x should not depend upon the total length, because the total length is downstream, right. The end of the plate is downstream. Okay. So, therefore, the boundary layer thickness at a given location x has to depend only upon x, the distance from the start of the heating section. It cannot depend upon the total length of the heating section. It can only depend upon the distance of that location from the start of the heating section. Okay. So, that we will use, okay, that we will use to say that we will define a similarity variable eta is equal to z by a boundary layer thickness which is a function of the x coordinate. Okay. Boundary layer thickness, that is a function of the x coordinate. Okay. And then we express the derivatives in terms of this. Okay. We express the derivatives in terms of this. Okay. Partial t by partial z. Okay, using differentiation by chain rule. Okay. And partial square t by partial z square is equal to 1 by delta square d square t by d eta square. Okay. Once again, differentiation using chain rule. Okay. Then there is partial t by partial x, okay, which is dt by d eta partial eta by partial x. Into minus z by delta square. Okay. The derivative of 1 over delta with respect to x is minus 1 over delta square times d delta by dx. Okay. And expressing it back in terms of eta, I can write this as minus eta by delta. Okay. So, we will use this expression for the diffusion term on the right side and this one for the convection term on the left side. Okay. So, therefore, Vs prime, okay, into z, which is delta eta, okay, into partial t by partial x, which is minus eta by delta d delta by dx into dt star by d eta. Okay, so, let me write it a little lower. Vs prime into z, that is delta eta, okay, into partial t by partial x, which is minus eta by delta d delta by dx dt by d eta. is equal to alpha by delta square d square T by d eta square. Multiplying throughout by delta square by alpha, multiplying throughout by delta square by alpha, we will get V s prime delta square d delta by dx, V s prime delta square by alpha into just cross multiplying the equation throughout by delta square by alpha. Now, we can get a solution of this which depends only upon eta for the temperature field. If we can get a solution for this which depends only upon eta for the temperature field if this term in the brackets is a constant. If this term in the brackets is a constant, we can get an equation for the temperature field that depends only upon eta. We require that V s prime delta square by alpha d delta by dx is equal to some constant c delta. Or alternatively, V s prime by 3 alpha d delta cubed by dx is equal to c delta. Or rather d delta cubed by dx is equal to 3 alpha c delta by V s prime. Or delta cubed into x plus a constant. What is the value of that constant? The value of that constant is determined from the condition that at the start of the heating section at x is equal to 0, at x is equal to 0 at the start of the heating section, that boundary layer thickness has to be 0 because there is no heat that has been transferred into the fluid as yet. There is no heat that has been transferred into the fluid as yet, and therefore, at the start of the heating section the boundary layer thickness has to be 0. Therefore, the condition is that at x is equal to 0, delta is equal to 0 implies that the constant d is equal to 0. And we get the boundary layer thickness as 3 alpha c delta x by V s prime. Or delta is equal to 3 c delta alpha x by V s prime whole power 1 by 3. So, this basically states that the boundary layer thickness increases proportional to x power 1/3. The boundary layer thickness increases proportional to x power 1/3 in the limit in this particular for the flow past a flat plate. Note that we had also got this boundary layer thickness, a similar calculation gave us boundary layer thickness increasing as L power 1/3 for the total length L. So, you are getting the same result from both the calculations. The other part is we have to calculate what is the temperature field in terms of eta, the temperature field in terms of the variable eta which we had postulated. That I will calculate in the next lecture. So, I will continue this calculation to find out what is the temperature field and therefore, the heat flux for the flow past a flat surface. We will continue this in the next lecture. I will see you then.